Okay, so for our warm-up then, which I kind of all smeared this in together because I, of course, wrote my objectives after I put my warm-up on the board. We're going to go through and find the angle of separation between the two. So ultimately, what are we going to be doing here?
Find the, is it the magnitude of the vector?
We're going to find the magnitude of each because ultimately we want these to be listed as unit vectors, and then we're going to be finding the dot product of the unit vectors. So, what is the magnitude of vector u? Or how can we find the magnitude of vector u?
Square root of u squared plus 4 squared plus 1 squared.
Good. It's square root of x component squared plus y component squared plus z component squared. So it is 3 squared is 9 plus 4 squared is 16 plus 1. That gives us, let's see, 25, 26. So the square root of 26. One thing that you probably have seen already in your math classes, but I like to point out is sometimes when you're performing operations on square roots and stuff and other radicals, if you want to show that that radical is close, you just put a little tail on it. So that's just kind of like math use. It's, you know, kind of like math slang, you know, maybe, I don't know. Okay, the magnitude of v then is the same thing. It's square root of the x component squared plus y component squared plus z component squared. So 9 squared is 81 plus 4 plus 9 gives us the square root of, let's see, that's 13, so 94. And so we know that these two vectors can be expressed as unit vectors by, I'll use my crazy notation again since we're in this vector u. So 1 over the square root of 26 times the vector 3, 4, and 1. And then the unit vector representing v would equal 1 over the square root of 94. Did I do that right? I could have swore I put 96 on my notes. I will just pretend like I did. 9, 2, -3. Alrighty, so, good there? So all this did for us was write them as unit vectors. Ultimately what we know is that if we want to find the angle between them, we can say that the cosine of that angle is equal to u over the magnitude of u, which is the unit vector representation of u, dot v over the magnitude of v. And this is commonly just written as u dot v over the magnitude of u times magnitude of v. I didn't bother to, or I didn't think to check the notation on this. Ian pointed out that from book to book, they sometimes use double bars versus single bars to represent magnitude.
Oh, I think that was Stephanie.
Oh, okay, sorry. I don't know why I would confuse you with Stephanie. But I'm really not sure. Anyhow, so, but anyhow, I will try to remember to check notation just to make sure I have it consistent, you know, so that I'm not conflicting with what the math department is teaching that down there. So at this point, we can go through and say that our angle of separation, alpha, is going to equal the arc cosine of the dot product of u and v, v all over the magnitude of u times magnitude of v. Let's see, what is the dot product of those two vectors?
Do we treat this the same? In the other example, we had a row vector by a column vector. I'm assuming it's
We
the same
would.
thing.
So in this case, in order to make the mathematicians happy, we would go through and say that, wow, that's a surprisingly large bracket. We would say that U dot V is going to equal row by column. So we have to express V as a column vector in order to keep all the mathematicians off our back. And in this case, what is the dot product? 32. It would be 3 times 9 is 27, plus 8 is 35, minus 3 is 32. So 32. So we have the inverse cosine of 32 divided by, let's see, it's square root of 26 times the square root of 94. And so what do you guys get there? Or is your calculator on summer break? I wouldn't blame it, I mean.
59 point something, point 4? I don't know if that's right though.
49.4?
Yeah, I got 49.4, so. Okay, so we have a 49.4 degree angle, and remember that, again, this can be kind of tricky to actually see and measure, because when we're representing this on two-dimensional space, it's very straightforward, but in 3 dimensions, we're trying to project the image out of the board. At least one of the, sorry, that's really low, that's just 49.4 degrees, so. Okay, so let's see how successful I am here. So we'll draw our z-axis, let's see, oh, maybe I should start drawing that old z-axis last. Try this again. Do you think it'll really matter? Probably not, I'll probably still miss it. Ugh. Oh, hot dog, look at that. So this is our plus of z. Where do our x and y's go? I thought for just a second that was a letter ring. that would have been amazing. It's like, wow, the alternative. Yeah. So, okay, so go ahead.
Is it anywhere? We just have to have them in
Okay.
order.
So if x is here, then where does y go?
Has to be to the right.
Right. Y has to be to the right as you're using the right hand rule. So this would be our plus y then. Okay, so unit, or I'm sorry, vector u would come along here, 3 in the x direction, and then 4 parallel to the y-axis. So 1, 2, 3, 4, and then 1 unit up. So our u vector is going to look something like that. And what we can do sometimes to help us recognize that is we can actually look at the projection on the xy plane to help us recognize the fact that it is in fact pointing out into space. I don't know if that really helped a whole lot or not, but the intention is there, so. Okay, our other vector then goes along the x-axis by 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Over 2 along the y-axis, so 1, 2, and then down 3. So this is 1, 2, 3. So in this case, I should probably have a yardstick in here. Let's see, that does seem to be perpendicular or parallel to the y or z-axis. So here is our v vector, and Somehow I have the opinion that by drawing it twice, it helps things, but I doubt that's actually the case. And then our projection on the XY plane would look something like that, just to give the impression that it is below that XY plane. So, and then of course the angle between them, which is what we just found, would represent the angle between the two vectors on the plane that's defined by those two vectors. That makes sense? This is much more to help us start visualizing the 3D coordinate system. We do, in fact, use this to a limited degree, particularly when we're talking about the Euler angles. But for the most part, we're just using this to get familiar with algebra, the linear algebra, and to start visualizing what this stuff looks like. You will see that when you're looking at the dot product, this is sometimes referred to as the directional cosine. Particularly when you're working with unit vectors. Okay, that directional cosine tells you the cosine of the value from one vector to another. So if this was, say, a reference line, the cosine of the angle of elevation off that reference line would be the dot product of the two, divided by the magnitudes. Make sense? For you, when are you taking your statics class?
In the fall.
Okay, so this will all come back and hit you again then. Are you taking it from Pringle, or have you signed up for it yet?
I have signed up for it. I don't remember when.
So like many engineers, if you do, I sat through Pringle's class, and I'll say like many engineers, if you take it from Pringle, he just treats math as part of the class. He doesn't really go in and explain the math. So I try to include at least a brief explanation of the math as I go through, because some of it we just haven't seen before, but not that that's necessary or needed or, you know, better. It's just the way I do things. So, so I tend to get kind of stuck on these things sometimes. So, okay, so does that kind of make sense there? Good. Okay, so the next thing we're going to do is go ahead and start reviewing matrices and get to the point where we can start actually defining frames. And this idea of a frame definition, particularly when we're using it to represent some kind of transformation, is what we're going to be doing for the next 6 weeks.
I just had a quick question before you list that. Because I don't know, it's basic. Is vector multiplication commutative? Like, could we switch those
No,
two
it's
around?
not.
Okay, so it's the same as...
Right, so, wait, oh no, let's see, okay. So, so scalar multiplication, actually I believe is, it's the cross multiplication that is not. So let's try that real quick. So let's go through and take, fudge. Yeah, actually it would be, wouldn't it? Because if we went through and said 9 to -3 dot 3, 4, 1, yeah, we'd be ending up with the same result, just the multiplication would take place in different orders.
So the way I'm used to thinking about it with matrices is you lay one
Right.
on top of the other.
So in the case of scalar multiplication or the dot product up to vectors, it is commutative. But we cannot assume that when we're dealing with matrix multiplication, it is not, because we're
Because
all...
you can just rewrite the vector in a column or row form.
Right. So. Yeah, and really the format that you're putting these vectors in is just a convenience thing. If we were to, and we'll take these two vectors here in a second, create a third vector and use that as a basis for a space. And when we do so, we can either express these as row vectors, which has a meaning in linear algebra, or more commonly in column vectors. Usually when we want to define a space, we're going to use column vectors to represent each of the vector definitions for that space. Okay, so going from here then, oh, and of course that was off the side of the camera, so I gotta watch that. Maybe what I ought to do, since I'm sure Liz doesn't have anything to do this summer, is I'll get her up here with a black marker and have her color this entire board black for me, and that over there. That way I'm not tempted to use it, so. She might actually have something to do this summer, so I'm not sure, so. What color do you guys want?
Let's go green.
Green? Okay, so yesterday we just started talking about matrices, and we gave an example of matrix multiplication. I'm not going to go through and do that again because hopefully that is old school from high school algebra 2 and math 153. But I will go through and start defining some of the more useful terms. First off, I think yesterday I mentioned a square matrix. It's nothing more than a matrix whose has the same number of rows and columns.
Can we just call that n by n?
That is an n by n matrix. Okay. Okay, so only square matrices can be inverted. Okay, and only square matrices can form a basis for a planar space. Any idea why?
I used to know.
So if we have too few matrices, or too few rows or columns in a matrix, then we're underdetermining that system. So if we are trying to define a space with two three-dimensional vectors, then ultimately what we're doing is forgetting to describe that third axis within our coordinate system. Okay? If we're over-defining it, if we're providing 4 vectors, then we're providing too much information. Okay? So what we want to do is we want to provide one vector of the appropriate size for each dimension that we're trying to define. If we're defining 4-dimensional space, then we want to have 4 vectors that have 4 elements in them. That makes sense? Okay. So, square matrix is going to be what all of our transformations are going to be based on. In fact, as I mentioned on Monday, our homogeneous matrix, which hopefully we'll get to today, will be 4 by 4 square matrix. Okay. When we go through and implement that in MATLAB, we're probably going to implement it as a 3 by 3 and a 1 by 3. So, and you'll see what I mean by that here when we get to it, hopefully later on here. So, let's see, after that, when we're going through and this is kind of unnecessary, but I'll say that if a matrix is invertible, then what we should see is that A dot A inverse had better equal A inverse dot A which had better equal identity in however many dimensions you're working on, okay? This means that when you hit a matrix with the inverse, it's the same as hitting the inverse with the original. In either case, you had better end up with identity. So if the square matrix is orthogonal, I'm sorry, orthonormal, then we can simply say that the inverse of A is equal to the transpose. Now, this is important because you can, in fact, transpose a non-square matrix. If we had, in fact, that's what we do when we convert a row to a column vector. Okay, all we're doing is changing the orientation. So if we had A, B, C, D, E, F, and we want to transpose that, then we're just going to stand it up instead of laying it down sideways like this. So we're going to do something like A, D, B, C, C, D, E, F. So we're just changing it across the, well, not the diagonal there, but we're just changing the rows for the columns. So this is the first row, it becomes the first column. This is the second row, it becomes the second column. Okay. In a special case where we're dealing with a square matrix that is orthonormal, we know that the inverse is equal to the transpose of that matrix. Yeah.
Could you define orthonormal again?
Orthonormal just means that each vector in the set is a unit vector and mutually perpendicular to the other two or others. Okay, so a classic example is I, J, and K form an orthonormal set because, of course, these are our three unit vectors that commonly define our Cartesian coordinate system, and they are all mutually perpendicular. How do we check for perpendicularity? We can check for perpendicularity by taking the dot product and seeing if it equals 0. Okay, so that's one of the things we can use the dot product for, is to see if two vectors are perpendicular. If they are, then we can just create a unit vector out of them and use them as a basis for our
So in terms of like spanning a space, these are non-spanning because they intersect, like.
Right, right. So that's kind of, I'm fearful of using that term because I always hated, you know, my, the professor that taught me linear algebra, for some reason insisted that I never got the term right, so, or never used it appropriately. So, but yeah, so when we talk about spanning a matrix or spanning a space, what we want to see is that each one of these are totally independent from the other two.
So we just say they're parallel. If they're
Right.
all parallel, then they span a space.
Yeah.
Okay.
Right. So, okay. So in this case, they don't have to be the unit vectors. In fact, they can be anything as long as they are mutually perpendicular and defined as a unit vector. So. A classic example is, like I mentioned before, a rotation matrix, which we'll get more into today. So, okay. Oh, and guess what? That's like the next thing on my list, so that's convenient. Okay. So, pretty much the next classic thing that we talk about, not that we're going to work with it extensively, but generally the next thing you talk about is determinants. And I'll throw determinants up here real quick, just so that allows us to discuss the cross product. The cross product is very useful to us. I will talk about determinants specifically as they relate to cross products. Anyone know what a cross product is good for? Turns out that the cross product, if you have two vectors defining a plane, the cross product can be used to define a vector perpendicular to that plane. And that's really nice because if we have two vectors, we can come up with a third vector to complete our set that we can define our space on. That makes sense? Okay, so the determinant you ever wonder why I don't just look how I spell it on my notes? There we go. Okay, determinant just determines the scale factor of a matrix. Okay, and that's kind of a weird term, but in fact, as you'll see, hopefully later today, how many times have I said that now? One of the things we want to do with this matrix is potentially change it around and so on and so forth. If we have a scale factor introduced into a matrix, then that means that potentially we could use this to zoom in and out on an object or resize an object if we wanted to. And the nice thing is that when you're looking at a virtual environment like a video game or something, and you scroll your mouse in and out, that's essentially what you're doing is changing the scaling factor of that particular matrix that is defining your point in space that you're viewing from. Okay. Well, in this case, the determinant is defined with the absolute value bars again. And if we go through and say that we have the determinant of A, we can go through and look at the elements within A. Okay, and with this then, what we can do within this matrix is we can start to break it down. One of the really nice properties of determinants is that we don't necessarily have to work with the entire matrix. We can work with what are known as minors of that matrix. Okay? For example, when we're working with a 3x3, we can actually look at each of the separate minors within that matrix. Okay? This is the minor of A11. These form the minor of A12, and so on and so forth. So what we can say is that the determinant of A can be expressed as a determinant of the entire thing, or it can be expressed as a sum of the determinants of the minors. So this would be A22, A23, A32, and A33. Okay, so we're going to go through and take this element and its corresponding minor. Okay, so we're going to take A11 times its the determinant of its minor minus A12 times the determinant of its minor. Plus A13 times the determinant of its minor, which is A12, 21, A22, A31, and A32. Now, part of the reason I bring this up is it is very useful and it falls right in line with what we're about to see. But on the FE exam, for those of you that plan to take it, they specifically will ask you to determine the determinant of the matrix. Who knows why, but on every practice exam and the FE exam itself, I saw a problem in which they said, find the determinant of this matrix. And if you go through and memorize the equation of the determinant, that's fine, but this is how it's expressed in the FE reference manual. Okay? So that's the reason why I teach it this particular way, and it is kind of a nice way to break it down. So what this then says is that we have A11 times the determinant of this guy. Now, do any of you remember how to find determinants? To find the determinant, you take the elements in the main diagonal and multiply them, minus the elements in the alternate diagonal and multiply them. And that's the reason why I break it down to a 2 by 2, because I don't like trying to remember the rules for a 3 by 3. So this would be A22 times A33 minus A32 times A23. And then we'd have minus A12 times A23 times A31 minus A33 times A21 plus A13 times A21 times A32 minus A31 times A22. And from there, I mean, we can plug in numbers all we want and get the job done. That's not the point here. What's up?
How do you determine, is it the first minor minus the second plus the third? Like
Yeah.
it staggers, right? I don't remember.
Right,
exactly.
so when you determine the sign, it's always plus, minus, plus, minus, plus, minus, plus, minus, plus. So you start in the upper right-hand corner. For me, I always define my determinant based on the first row. But the fact is, you could do it on any row or any column. You just have to make sure you have your signs plugged in right.
A lot of times you'll find a row with a lot of zeros and choose that.
Yeah, absolutely. So if you have like a column with a bunch of zeros or a row with a column with a bunch of zeros, then you can. If you have an entire row or a column with zeros, then the entire thing's going to turn out to be zero.
Yeah, you can.
Right. So, but if you just have a heavily populated row with zeros, for example, if A22 and A23 were both zeros, then we'd want to rotate this about A21, because then the other two terms would drop out entirely. So, what do you notice about the determinant? What type of quantity do we end up with?
Well, it's going to be a scalar.
Yeah, it is definitely a scalar, and the value of the determinant tells you a lot about the matrix. The only real thing we'll talk about here is that if that determinant is zero, then we know that that matrix is not invertible. Okay. Interestingly enough, if we could say almost that if the determinant is 1, then we have an orthonormal set. That makes sense? Because presumably that orthonormal set is composed of unit vectors, and therefore when we go through and find the determinant, we should end up with a scaling factor of 1. If we have a vector composed, as we did earlier, just of a bunch of random vectors, those, the scaling factor will be large. Okay, so one of the other things that we can, I'll say about this is that for those of you that may have taken an engineering class back in the 90s, the determinants were used heavily to go through and solve systems of linear equations. And particularly when people were working with these solutions, they applied what's known as Cramer's law or Cramer's rule to those systems. Cramer's rule takes heavy use of the determinant in solving the systems. Anymore, we don't apply Cramer's rule because, well, now our calculators can directly apply Gaussian elimination, which gets the job done a lot quicker. So Gaussian elimination is a much more efficient algorithm than what this is. In fact, I think it's several orders of magnitude more efficient than Cramer's rule. So maybe not several. It would, of course, depend on the size of the matrix, but it is significantly more efficient than Cramer's rule. So, okay, so this gives us a good introduction to determinants. Now, to take a look at how we're going to, or why we need to know something about them. And that is for the part, or I better fix that. No, I tried. For the cross product. Okay, the cross product is known as the vector product. I'll put AKA vector product of two vectors. The result of this cross product is a perpendicular vector to the plane defined by the known two vectors. Okay, so as we saw a minute ago, I shouldn't have erased our drawing, but in the case we saw a few minutes ago, we had one vector shooting down here, another vector maybe shooting something like this, and this represented the plane that we were defining. Well, if this is heading down here, well, the perpendicular vector might look something like that. Okay. Notice that these are not orthogonal vectors, but we could still go through and define a perpendicular vector from that to define our three vectors that would, or could be used to define our space. Okay. So in order to find the cross product, well, first off, the symbol used to define the cross product is the X. Sometimes you say the X with a circle around it just to make it stand out and distinguish it from straight multiplication. But commonly, if you see U cross V, this is specifically talking about the cross product. Okay. When we go through and do this, well, in order to perform a cross product operation, we have to calculate a determinant, and this is kind of loosely defined, okay? And you'll see why here in a second. The cross product is defined as the determinant of I, J, K in our first row, Ux, Uy, Uz in our second row, and then finally Vx, Vy, and Vz in our third row. Why am I saying that is loosely, or why our cross product is loosely defined this way? Well, we'd have to treat these as variables in order to make this work, right? we know that these are in fact vectors themselves. So we would end up with what, a 5-row by 3-column matrix if we were to fully populate, if we were to fill in what I, J, and K actually mean. But if we just treat these as variables, then we can go ahead and perform this cross product operation. So using the same idea that we just did, what is the cross product going to equal?
So it'll be I multiplied by U sub Y, yeah, that.
Yeah. So it would be I times the determinant of this matrix minus J times the determinant of its minor, and plus K times the determinant of its minor. Okay, so we have I times the determinant of UY, UZ, BY, BZ, minus J times the determinant of its minor, which would be UZ, UX, BZ, BX, plus K times the determinant of its minor, UX, UY, VX, VY, and I suspect that'll be off the point there. What type of quantity do we end up with? We end up with a vector of the same dimensionality as what we started with. The resulting vector will have the same dimensions as the original vectors. Okay? So let's say that we have the same boring vectors that we started the day with. Our U vector is something 3-1 or 3-4-1. V is equal to 9 to -3. Go ahead and spend a minute or two figuring out what the cross product is of U and V. Oh, and there is one really cool property here that I'll point out in just a second. So. Alrighty, so what did you guys get there?
I got the same.
So let's see, the determinant of the first minor is -12 minus 2, so -14. So we end up with negative 14i. And then we have 9 minus a negative 9. So 9 minus negative 9 is 18 times a negative 1. So we end up with a negative 18j. And then 6 minus 36 is negative 30. And that's just a negative 30j. Did I do that right? Or
I could have messed up. I don't know. In the I, was that v sub y? Is that not 9 or this, in the first vector, the 9? I thought it was the x.
v sub y. So v sub x is
9.
9, v sub y is 2, and negative 3 for v sub
So
z.
in the I, v sub y is the,
Oh, geez, then, so,
I got the same thing as you.
yeah.
okay. Well, then we'll just assume we're right. Well, that seems, okay. So one thing I'll say is that if you have a hard time filling in your matrix, what you can do is, when you go through and determine the matrix, what you can do is just copy over the first two columns. So A, B, D, E, G, H. And what this allows you to do then is, let me do this. I'll use these brackets to indicate the minor there. And then C has the minor of, well, maybe I should use a different color, since I have different colors. And then finally, like that. So we can use the 5-column approach just to make sure that we're filling out the determinant and identifying the minors properly.
No, I looked at the wrong spot in the vector
Oh.
for x and y, so I had to flip around.
Yeah, that's something that, you guys probably saw that in the pre-calc one, right?
It's been many, many moons
Yeah.
since pre-calc 1.
Yeah, yeah. And it should have been there, if not, it's just one of those things that, you know, it's something most instructors touch on, even if it's just, you know, real quick, but not something we necessarily have to get real stuck on. Okay, so how can we interpret that as a actual vector then? Well, we have, let's see, negative 14 times I, which we know is 1, 0, 0, minus 18 times j, which we know is 0, 1, 0, minus 30 times k, which we know is 0, 0, 1. So we could just interpret this as negative 14, because only the x component, if you will, is being hit with a negative 14 here. Only the y component is being hit with a negative 18 here. And only the z component is saying the negative 30. And so that is the vector perpendiculars in that plane. Yeah.
And we got those IJK values from the identity, correct?
Yeah. So this is just how we set up the determinant in order to find the cross product. We put I, J, and K in the first row, and then we put our U vector in the second row, our V vector in the third row. Okay. Now here's something that's kind of cool. What do you suppose? One of the really nice properties here of this is what do you suppose V cross U is? We just calculated u cross v. Turns out it's just negative u cross v. Why is that? Think about it geometrically. I'm going to cheat and say that our u and our v vector are easy to represent, and we have our u cross v here. Well, what we're doing when we're doing u cross v is we're looking at the vector from u to v. Okay? If we go through and do a v cross u, then we're looking at v to u. So which direction are we pointing in? The other direction. Okay? So that's one of the really cool things that is surprisingly easy to, or relatively easy to interpret geometrically. Okay? If we go u cross v, we're just pointing in the upward direction. If we reverse that and do v cross u, we're pointing in the negative direction. So notice how our cross product in that case had a bunch of negatives in it. Well, we could avoid that just by doing v cross u instead, if we so decided to do so.
Would that just change all the signs?
Yeah. Okay, so this gives us a really, maybe not a really good introduction to the linear algebra that we'll need, but it gives us enough linear algebra to start understanding some of the information that we have available or that we'll need for this class. So now let's actually get started with what we'll be doing in this class. And to start this discussion, I will take a step back and revisit the concept of a frame. What did I define a frame as on the first day of class?
The description of position and orientation.
Exactly. So, a frame is a description of position and orientation. Okay. Sometimes this description is with respect to another frame. Sometimes this description is with respect to a universal coordinate system, like the Cartesian coordinate system. So, to the universal coordinate system. Okay, so ultimately, for our robot, the local frame that we'd be defining, everything with respect to, hopefully, would be the center of the base axis. Okay, we want to position that so that we have a known x, a known y, and the z radiates from the center of that axis of rotation. Okay. Now that doesn't necessarily mean that that's the universal coordinate system, but for the purposes of this robot it is. Ultimately, I don't think there's probably anyone that could tell you what the universal coordinate system is reference to. So probably some people that you know, assume they know, but I doubt they really know, so. Okay, so if we're defining a frame, let's go through and look at first position vectors. This is going to seem pretty trivial, but a position vector describes a position within a frame. And what we do when we want to reference this is we say that this position vector is described in frame A. So P is described in frame A. Okay, why is that important? So if this is our P vector, and it's pointing at a point here, well, why would we want to make sure that we tell everyone that it's being described in terms of frame A?
Well, we could have like another linkage in that second space he defines, and it's gonna have to take that into account.
Exactly, because if this is the link, or I'm sorry, if this is the joint described in one position, well, that position relative to the next joint is going to be defined differently. In this case, this would describe the position vector in A, but this would describe the same position vector described in frame B, okay? So that's very important to keep in mind. I mean, if we know something about a position vector, that's great, but we have to know which frame it's referring to. We can ultimately think of these frames simply as what the definition of each of these joints is, you know, how we're defining each of these joints, okay? Now, sometimes you see a subscript as well as a leading superscript. So, for example, okay, how many of you have started reading the book?
A little bit.
It's kind of a troubling book to read. I mean, the guy that wrote it, you can tell it's just an incredibly smart guy, but some of his notation is really kind of cumbersome to keep straight, okay? He does, however, use this notation quite often. So in this case, he's saying that P is described in A to point at the origin of B. Okay, so essentially what he's saying is this P or B so that would be our position vector of the origin of B in terms of A. So this is very literally how we would describe the displacement from this joint to this joint, just as a position vector from joint to joint. Okay. Now what we want to do is we want to make sure that that position vector is along a single axis. So when we go through and set this up, we make sure that that is a X translation or a Y translation or a Z translation. That way we can really simplify the way our mathematics is set up when we are establishing our kinematic